Debian, the universal operating system, is getting a huge security win for Debian 14, and that security win is reproducibility. So Debian 14 is going to be making reproducible builds a mandatory thing with their packages. So reproducible builds are now a hard requirement for packages in Debian 14. So any package failing a reproducibility test will now be blocked from Debian testing, which is the repo that they use to sort of develop Debian 14 alongside Unstable too. And any package that appears in Debian testing that breaks reproducibility in an update is actually going to be blocked from the repo. So this is essentially forcing a transition of the package base to become reproducible. Now you may be wondering, what is reproducibility? Well, this is the definition from reproduciblebuilds.org. A build is reproducible if given the same source code, build environment, and build instructions, any party can recreate bit by bit identical copies of all the specified artifacts. So an artifact would be like a binary. If you're coming from Windows, essentially the executable of whatever the package is. But Cameron, isn't that how, I don't know, source code works? You have instructions and the compiler takes them all and produces a binary from those instructions. Well, that is like saying that baking a cake with the same recipe produces the same result every time you do it. That isn't how baking works. You have a bunch of different variables. Your ingredients could be varying levels of quality. Maybe your oven isn't very good. I know in the dorms I had the worst oven ever. The point is, if you're actually building from source code, there are a lot of different things that can actually affect the outputted binary alongside the code. It could be the version of the compiler you're using. It could be timestamps being different when compiling. It could be maybe on some file systems, the files get read in a different order and it affects how the binary is produced. It could be different dependency versions when you're actually building the project. And while most of these things may not introduce any functional difference in how the code runs, it does make the binary technically different from other binaries from other people compiling the code. And what we want here is we want every binary to actually be the same. Bit for bit identical copies. Now, why is this so important? Well, the reproducible-builds.org website has a pretty good page on why this matters. Now, I am going to read this in a different order than this page has just for the sake of flow of the video, but let's start off with dependency tree awareness in software bill of materials, aka SBOMs. So reproducible builds significantly enhance the transparency and integrity of software development by making sure developers have complete awareness of the dependency tree, ensuring all the dependencies are exactly as intended without any undisclosed changes or additions. This level of control is crucial for security as it helps in identifying and mitigating vulnerabilities that often reside in overlooked components. So part of this is a software bill of materials, which is essentially a list of all of the software you have and what version it is running. These are indispensable for regulatory compliance, vulnerability management, and risk assessment, making reproducible builds not just beneficial but essential for maintaining software integrity, reliability, and security in the face of evolving cyber threats and regulatory requirements. So this is very good because if, for example, you have a vulnerable piece of software in the dependency supply chain or even like a backdoor or something, everyone knows what version is on their system from the software bill of materials, and they know that they need to go and mitigate it. And that's just one use of software bill of materials here. Next up is increased development speed. Dependent packages do not need to be rebuilt and dependent tasks do not need to be rerun if a rebuild of a package does not yield different results. This can significantly reduce build times and lead to a faster development speed and lower cost. And then you're also just going to have smaller differences in the binaries that are produced when you actually compile a project. So having reproducible builds means that only changes in the source code or build environment will lead to differences in the generated binaries. So this is going to reduce storage requirements and network traffic for delta updates, which are updates where the only thing being pulled in is actually the difference between two versions of a package rather than the entire new package getting pulled in. And then testing can focus on parts that change while preserving confidence about unchanged code. And this helps with quality assurance. And speaking of quality assurance, regular tests are required to make sure that the software can be built reproducibly in various environments. So Debian and other free software distributions require that their users must be able to build the software they distribute. Such regular tests help in avoiding fail to build from source bugs and can uncover rare build problems such as timing problems, race conditions, or builds affected by locale. So far, all of the reproducible build stuff mainly helps with developers because they don't have to worry about differences in the binaries that are actually shipped compared to what they're able to build, and just quality assurance in general. But there's another huge security point here, and that is resisting attacks. So this article points to a CIA exploit called Straw Horse, where they were basically shipping out malicious versions of Xcode that would insert spyware into compiled applications, and then app developers using this pwned version of Xcode would unknowingly distribute malware. So this is called compiler malware. And part of the purpose of reproducible builds is exactly to resist such attacks. Recompiling these applications with a clean compiler would have made the problem easily visible, especially given the size of the added payload. So what this is saying is, if distributions have reproducible builds and then you go and run the reproducible build, if either party was using a pwned compiler, for example, then it would have been caught when the person testing it is comparing their binary with upstream and they see differences. And then they can figure out that the differences are either that upstream has been hacked or that they have been hacked. Now, you may have remembered the XZ-utils backdoor, where basically this malicious contributor to the XZ compression library for Linux, they did this whole trust building campaign and became one of the core maintainers of the project, and then they tried to implement a backdoor into XZ that would basically give them SSH access into any Linux server in the world. Now, the thing about this backdoor is that the person doing it would have gotten caught if they just were to git commit a backdoor straight into the XZ project, because XZ, this is a core Linux dependency, it has a lot of eyes on it, and someone would have audited the source code and immediately found the backdoor, probably as soon as it is git committed and git pushed. However, this exploit actually ran a script at build time of the project that would inject code into XZ, into the binary, again, at build time. So this malicious code wasn't a part of the source code, but this one testing file is actually able to inject things into the actual artifact, this being XZ, to get this backdoor into the project without anyone seeing it. And notably, this script would only perform the injection if the system was being built on an x86-64 architecture using glibc and GCC and being built through DPKG or RPM. Now, if reproducible builds were enforced, the tarball that they distributed to distro vendors wouldn't have been able to produce the same binary that actually using just the source code of the program would have generated. And so when the binary doesn't match the publicly verifiable non-vulnerable source code with the backdoored binary, then the XZ backdoor would have been caught immediately rather than it being shipped into a testing repo and a Microsoft security researcher finding it because they found a performance regression in Debian SID. Are there any catches to this? Actually, pretty much the only catch to reproducible builds is that it is a lot of work to get the entire Debian package base to actually be reproducible. That is a lot of time and effort for packagers and Debian developers to do, but from the end user perspective, there isn't really a catch to this. This is just good news. Now, what's the current progress with this? Well, if we go to the page that Debian has for reproducibility, we can see that about 98.31% of the packages that are built for all architectures, so that is usually interpreted languages like Python, Perl packages, there's only 407 packages that are not reproducible yet. And then if we go to AMD 64, which is what the majority of computers run, minus like ARM Macs and mobile phones and Raspberry Pis, for those packages we are at 97.49%. I'm not going to go into the other architectures, but we're most of the way there. That said, all the packages that are not reproducible yet have good reasons for not being reproducible yet and may take some additional work to actually get these to be reproducible. It's not as easy as just making a package reproducible. So if I go to the AMD 64 right here, these are all problems that prevent certain packages from being easily reproducible right here. That said, Debian is one of the first major Linux distributions to commit to 100% reproducibility. There is NixOS and Geeks too. Those are 100% reproducible, but the difference in that is Geeks and NixOS are both declarative operating systems, so they were designed to be reproducible from the beginning. They aren't doing these large migrations to actually be able to do this. Tails is another operating system that is 100% reproducible, but this also makes sense for their project goals because this is a privacy-focused operating system designed to protect against surveillance and censorship. They don't want some sort of backdoor put in their operating system somehow, and using reproducible builds, as I said earlier, is a great way to prevent that. But out of like base Linux distributions, out of like Debian, Ubuntu, Fedora, Arch, Debian's the first one to commit to 100% reproducibility reproducibility. And this is a pretty cool trend, although it isn't the first major distribution to start the transition to reproducible builds. Going back to the reproduciblebuilds.org website, we go to who is involved right here, and let's go to projects. There's tons of different projects involved, not just Linux distributions, but things like Apache Maven, Bitcoin Core, Core Boot, the Free Desktop SDK, the Go programming language, Monero, Tor browser, and several other projects. And then in terms of Linux distros, we have Alpine, we have Arch, obviously Debian, that's what we're talking about, Fedora, FreeBSD, that's not Linux, but it's an operating system, Geeks, as I mentioned, NetBSD, NixOS, OpenSUSE, I think OpenYure is a Linux distro, Cubes, I already mentioned Tails, Taos Linux, Trisquil. So yeah, this is a recurring trend in the Linux space, and it's kind of cool to see Debian to be the first to do something, although it makes sense because this isn't something that's going to make Debian unstable. And this just improves the package platform that Debian is building for their operating system here. They're trying to be the universal operating system, and this is just an initiative that just straight up just improves their packaging platform. So with that, tell me what you think of these reproducible builds. If you like this video, you can shoot me a sub right here. Help support a broke college student on Patreon. And on the topic of cybersecurity, right here you can watch my video about how AI has broken cybersecurity. With all of that, I'll see you guys in the next video, and peace out.